The night sky appears still. The stars look fixed. The darkness between them looks empty. But the impression of silence is created by the limits of human senses, not by the true nature of the universe. Space is active. It is filled with motion, charged particles drifting through magnetic fields, shock fronts expanding from stellar explosions, and radiation crossing immense distances without slowing. The universe does not speak in language, but it does produce patterns, signals that can be detected, measured, and studied. In this episode, attention shifts from the message humanity sent outward, Voyager's long journey beyond the heliopause, to the unintentional messages that arrive from the cosmos. These are not replies in the human sense. They are not directed communications. They are the byproducts of natural processes, many of them extreme, many of them unfamiliar, and some of them still not fully understood. In this episode, the focus is on the signals that stand out against the background, pulses, bursts, repeating events, and anomalies that have captured scientific interest for decades. The goal is not to dramatize them, but to understand why they are surprising, how they are verified, and what they reveal about the universe. Welcome back to Beyond Space. Where we explore the universe one mind-blowing idea at a time. To understand why signals from space can feel mysterious, it helps to begin with a foundational reality. The universe communicates information through electromagnetic radiation. Light is only one small portion of the electromagnetic spectrum. Beyond visible light, there are radio waves, microwaves, infrared, ultraviolet, X-rays, and gamma rays. Different astrophysical processes produce radiation at different wavelengths. Some of the most energetic and violent events in the universe are best seen in X-rays and gamma rays. Many of the most subtle and long-distance signals travel through radio frequencies. This episode concentrates on signals detected primarily through radio astronomy, not because radio is the only window into cosmic phenomena, but because radio signals have a distinctive quality. They can travel long distances, they can carry precise timing, and they can reveal processes that are otherwise hidden. But before any mysterious signal is discussed, it is essential to understand the first and most common explanation for unusual detections: interference from Earth. Earth is noisy. Modern civilization emits radio waves constantly. Communications networks, satellites, radar systems, aircraft transponders, even some household electronics. These all contribute to a background of human-generated signals. A radio telescope is not only a cosmic ear, it is also an antenna in a technologically active environment. For this reason, the first assumption in professional astronomy is not that a strange signal is exotic. The first assumption is that the signal might be local. In this episode, one of the most important points is that mystery often begins with verification. When a signal is detected, researchers ask a series of calm, practical questions. Is the signal coming from a fixed position on the sky, or does it move in a way consistent with a satellite? Does it appear in one telescope or multiple telescopes? Does it repeat? If so, does it repeat with a pattern that resembles human technology? Does it occur at a frequency band known to be contaminated by terrestrial transmissions? Could it be a hardware artifact? A calibration error? A software issue? Is the signal consistent with atmospheric effects, such as ionospheric disturbances? Only after these questions are addressed does a signal remain interesting in an astrophysical sense. This process is often invisible to the public because it lacks drama, but it is where most mystery signals begin and end. And yet, even with careful verification, some signals remain. They remain not because the universe is trying to conceal something, but because the universe produces phenomena that do not immediately fit simple explanations. One of the most famous examples is the WOW signal. In 1977, a radio telescope associated with SETI-related observation detected a strong, narrow-band radio signal that lasted for less than a minute. It appeared to come from a region of the sky near the constellation Sagittarius. The signal was unusual enough that an astronomer, reviewing the computer printout, circled the data and wrote a single word beside it: "Wow." The WOW signal became famous because it contained features that seemed compelling. It was relatively strong compared to background noise. It was narrowband, which is often associated with artificial transmissions. It lasted for a short time and then disappeared. It was not detected again. That last point is crucial. In science, repetition is one of the strongest indicators that something is real and characterizable. A one-time event is difficult to interpret because there are many possible explanations, including chance interference or rare natural phenomena that do not repeat on human timescales. The wow signal has been discussed for decades, and many plausible explanations have been considered. The most important conclusion is not that the signal represents extraterrestrial intelligence. The most important conclusion is that a single anomalous event is not enough to establish a strong claim. In this episode, the wow signal represents something else. It represents the human tendency to treat unusual patterns as meaningful. It represents how easily a brief, striking event can become a cultural symbol, and it represents a real challenge in astronomy. Some events are rare enough that they may not repeat during the window when we are watching. This leads to a broader point. Astronomy is largely observational. It cannot run controlled experiments on distant stars or galaxies. It must interpret signals as they arrive, often without the ability to repeat the conditions that generated them. That is why certain classes of signals, those that repeat reliably, are especially valuable. One of the most important repeating signals discovered in the 20th century was the pulsar. When pulsars were first detected in 1967, they appeared as extremely regular radio pulses, so regular that they resembled a beacon. The first detected pulsar produced pulses roughly every 1.3 seconds. The regularity was so precise that it triggered an immediate sense of disbelief. Early researchers briefly entertained the possibility that the signal could be artificial, and as a joke, partly to guard against embarrassment, they labeled it LGM for Little Green Men. This label is often retold because it sounds dramatic, but it actually illustrates a calm scientific principle. If a signal looks too ordered, it is worth considering all possibilities, including the unexpected. But it is also worth looking for natural mechanisms that can produce order. Pulsars turned out to be natural. They are neutron stars, remnants of massive stars that ended their lives in supernova explosions. A neutron star packs more mass than the Sun into a sphere roughly the size of a city. The density is extreme, the gravitational field is strong, the magnetic fields are often enormous. Many neutron stars spin rapidly, some rotate multiple times per second. Their magnetic fields funnel charged particles and radiation into beams that emanate from their magnetic poles. If the magnetic axis is tilted relative to the rotation axis, these beams sweep across space as the star spins. From Earth, this looks like a pulse, a cosmic lighthouse. The discovery of pulsars did not remove mystery from the universe. It transformed mystery into understanding, and then into utility. Pulsars are so regular that they can function as celestial clocks. They are used to test general relativity, to detect gravitational waves indirectly through timing arrays, and to probe the interstellar medium. In some navigation concepts, pulsars could even serve as reference points for spacecraft position determination. In this episode, pulsars represent a key theme. The universe can produce signals that feel engineered simply because physics can generate extremely stable periodic behavior. If pulsars show that order can be natural, then a related category of signals shows something else. The universe can also produce events so brief and intense that they feel like a shock. These are fast radio bursts, or FRBS. Fast radio bursts are intense pulses of radio energy that last only milliseconds. The energy involved is enormous. The bursts are so short that early detection was difficult, and for some time they remained rare and puzzling. The first FRB was discovered in archival data, which meant it was found after the fact, an event recorded by an instrument recognized later. As more FRBS were detected, they raised immediate questions. What kind of astrophysical object can produce a burst that bright, that quickly? How can a signal travel across cosmological distances and remain sharp? Are FRBs produced by catastrophic one-time events or by repeatable mechanisms? At first, many FRBS were thought to be one-off events. That led to hypotheses involving catastrophic sources, collisions of compact objects, explosive stellar deaths, or other singular events. But then, a major shift occurred. Some FRBS were found to repeat. A repeating FRB changes the landscape because it implies the source survives the event. This rules out many catastrophic explanations and pushes the focus toward mechanisms that can generate bursts multiple times. One of the leading candidates involves magnetars, a type of neutron star with an extremely strong magnetic field. Magnetars can undergo starquakes and magnetic reconnection events, releasing energy in sudden bursts. In certain conditions, these events can produce radio bursts consistent with FRB behavior. But even within magnetar explanations, there are open questions. Why do some sources repeat and others do not? Why do the bursts cluster in time for some repeaters? What role does the local environment, plasma, magnetic turbulence, surrounding material, play in shaping the signal? In this episode, it is important to maintain a calm perspective. FRBs are not mysterious because they suggest intention. They are mysterious because they sit at the boundary of what is easily modeled. They are a window into extreme physics, dense matter, strong magnetic fields, relativistic particles, and complex plasma environments. And there is another reason FRBs matter. Even before the source mechanisms are fully settled, FRBs can be used as probes of the universe. As radio waves travel through space, they pass through ionized gas, plasma. This plasma causes dispersion. Lower frequency waves travel slightly slower than higher frequency waves, spreading the pulse in time. By measuring the dispersion, scientists can estimate how much ionized material the signal passed through. This means FRBs can reveal the distribution of otherwise invisible matter in intergalactic space. They can help locate missing baryons, ordinary matter that is difficult to detect directly, but is expected to exist based on cosmological models. In other words, a mysterious signal can become a tool for mapping the universe. This pattern repeats throughout science. First, a phenomenon is detected, then it is verified, then it is explained, then it becomes useful. But not all signals are bursts and pulses. Some are steady, some are modulated. Some come from rotating objects or binary systems. Some are produced by planets interacting with stellar winds or by the magnetic environments of stars. The universe is a generator of radio emissions, and radio astronomy is the art of translating those emissions into physical understanding. In this episode, the emphasis is on signals that stand out enough to generate broad interest. Pulsars and FRBs are two of the most important. The wow signal is culturally significant, but the landscape is broader. There are also signals that are not far away in a cosmic sense, but that still carry mystery because they represent boundaries. The boundary between known astrophysics and something that could be new. For example, there are cases where signals appear to come from unexpected places or behave in ways that don't match known categories. Sometimes these cases are resolved as instrumental artifacts. Sometimes they are resolved as new examples of known classes. Sometimes they remain uncertain until better data arrives. The key is that uncertainty is not failure. Uncertainty is the natural state at the edge of knowledge. This is also why astronomy relies heavily on networks and replication. A detection in one instrument is useful. A detection confirmed by multiple instruments is stronger. A detection repeated over time and studied across multiple wavelengths becomes a robust source. This is where a calm documentary voice becomes valuable. It allows the story to remain grounded in how science actually works. Signals do not become significant because they are exciting. They become significant because they persist through scrutiny. Now, the episode's connection to Season 1's broader arc becomes clear. Episode 1 focused on Voyager crossing the heliopause, leaving the sun's bubble and entering interstellar space. That transition is not only symbolic, it is a shift into a region where the solar system is part of the galaxy's broader environment. The galaxy is filled with radiation and particles. Interstellar space is permeated by cosmic rays and shaped by magnetic fields. The heliosphere itself modifies the flow of these particles into the solar system. This means that signals from space are not purely distant in origin. Some are shaped by the boundary region Voyager measured. Some are affected by the interstellar medium and the plasma between stars. Even when signals originate in distant galaxies, they must travel through intervening material. Their characteristics carry the imprint of that journey. So signals do two things at once. They reveal the source, and they reveal the space between the source and the observer. This is a powerful idea. A signal is not only information about where it came from, it is also information about what it passed through. This becomes especially relevant when considering the next step in the season. Signals, by themselves, can be fleeting, they can be hard to interpret, they can be dramatic but short-lived. To move beyond signals into a deeper understanding of cosmic history, another approach is needed. Seeing. Not in the sense of human vision, but in the sense of imaging, collecting light across time, across wavelengths, and across the early universe. That is why the next episode will focus on a machine built not to capture brief bursts, but to stare into deep time. The James Webb Space Telescope. Webb is not primarily a radio telescope. It is an infrared observatory designed to capture ancient light that has been traveling since the universe was young. But the connection to this episode is direct. Signals tell scientists what is happening now in extreme environments. Webb tells scientists what happened long ago, during the formative eras of stars and galaxies. Together, they create a layered understanding of the cosmos, dynamic events in the present, and deep structure in the past. This episode has described how signals can be verified and understood, and how the universe can produce patterns that resemble engineered behavior. It has also shown how mystery can be transformed into measurement. The next episode will carry that theme into an even larger context. Because Webb's observations, like many great instruments, do not simply fill in details. They challenge assumptions. They reveal a universe that may be more complex early on than expected, full of structure, full of surprises. And behind that structure lies gravity, often in its most extreme forms. The season's arc is moving from the message humanity sent outward, to the signals the universe produces, to the early light of cosmic history, and then toward the most extreme gravitational objects that shape galaxies. In this episode, the universe is presented as an environment full of signals, not messages in a deliberate sense, but patterns produced by natural processes. The lesson is quiet but significant. The universe does not need intention to be informative. It does not need consciousness to produce patterns, and it does not need to speak in language to be heard. The act of listening, carefully, patiently, turns noise into knowledge. And as instruments improve, the universe becomes less silent, not because it changes, but because the ability to perceive it expands. In the next episode, that expanded perception will take the form of an infrared eye placed far from Earth's atmosphere, designed to see what was previously hidden. In this episode, listening revealed that space is not quiet. In the next, seeing will reveal that the early universe was not simple. The signals continue, the story deepens, and the darkness becomes slowly more legible.